So, hello and welcome to my class. Let me first set it in the full screen mode. As I told you in my last class that I'll be teaching you the CC2, the Core Course 2 paper mostly. And so let us start with the first formal class. So it starts with Unit 1, that mostly concerned with complex numbers. So we will do a certain recap of complex numbers. You must have done some extensive studies on complex numbers in your 10+2 level. So in the first class, we will be doing some recap or brushing up your memories of complex numbers. So let's start with some standard notations of sets which we will be using throughout this class and throughout the session, and these are the standard notations that you must be familiar with. So let's start with the first one, that is this n. N stands for is the set of all natural numbers, but the n, that universally accepted notation, is something like this. So you must be knowing these notations like this. Natural numbers are like 1, 2, 3, etc. Then comes the set, the integers z, which includes 0 and the negative natural numbers. And then the rational numbers, you know, the set of all rational numbers are like the numbers which can be represented in the form of p by q, where q not equals to 0 and p and q are mutually prime. That means there is no common factor between p and q. Such numbers are called rational numbers. You must be knowing all this. And then comes the number called the real numbers. It includes all such numbers, all the above numbers, including some numbers which are not rationals, like √2, √3. Okay, these are not rationals, but they are real numbers. So the hierarchy of these sets are like this. The natural number set is a very small one, and then comes the integer set, which includes the natural number, and then the rational numbers. The rational number is slightly bigger than the set of all integers. It includes all the natural numbers, integers, and some more numbers like the fractions of the form p by q with certain properties. And then comes the set of all real numbers. That includes the rational numbers as well as some numbers which are not rational. We will call them irrational numbers. We will study them also in a separate topic in a separate class. Okay, so real number is the biggest thing here. And we also know that these real numbers can be represented as points on an infinitely extendable line, and such line is called real line. You know, you have studied that. Usually it is the x-axis. You have been taught that x-axis is considered as the real line, where each point on the on the x-axis represents a real line. Everything can be represented as a point on this x-axis. So x-axis is considered as real line, and in particular real numbers can be represented as points on x-axis or an infinite line. Now, the life was so simple, and we had real numbers. We knew everything about real numbers. And why do we need complex numbers? What is the need of such thing? Well, now let us look certain quadratic equations. An equation of the form x square equals to 2. Now, if I ask you to solve this quadratic equation, that means if I ask you to find out the roots of this quadratic equation, you will definitely come up with an answer like this. X will be plus minus √2, plus √2 or minus √2. If you square them, you'll get 2. Well, it is fine. But if I ask you to solve an equation of this form, x square plus 2 equals to 0, you will get a quantity like this, plus minus root over minus 2. In particularly, minus 2 can be written as 2 into minus 1. So √2, that part is real, that is that something that you know. So take it out and you are left with some quantity of this form, root over minus 1. Now, what is this root over minus 1? Right? Well, root over minus 1 is real. Of course, it's not something which is real, so it's not a real number. And here comes the complex numbers. This is called the unit complex number. That's the beginning of the complex numbers. And any multiple of root over minus 1 gives the other complex numbers. So in particularly, if you add a real number to a multiple of root over minus 1, that is also a complex number. So you start getting whole lot of numbers of the form a plus ib, where a, b are real. See, a is a real number, you add to it the real multiple of root over minus 1, that's I. I is the universal notation for root over minus 1. You must be knowing all these things. And you get a whole lot of numbers which are not real numbers. And you know, this collection of such numbers of the form a plus ib, where a, b are real numbers, but I is something which is not real, and the collection of such numbers is called the set of all complex numbers. All right, and if you remember, then a is called the real part of the complex number a plus ib, and b is called the imaginary part of the complex number a plus ib. So real part is a real number, imaginary part is also a real number, which is the multiple, the factor, the multiplying factor of I in the complex number. So real part, imaginary part of a complex numbers. You also have noted something, that real numbers are actually embedded inside the set of all complex numbers. How? Any real number alpha can be written as alpha plus I into 0. So this part actually goes, it doesn't appear with alpha, but it is hidden somewhere. So any real number can be written as a complex number of this form, alpha plus I into 0. So any real number is also a complex number. So real number, the set of all real number, which was more or less a very big set so far we have considered, is even a subset of the complex numbers. So complex number is a much larger set than the real numbers. In fact, in the course of your studies, you will see that C, this complex number, well, by the way, the set of all complex number is denoted by C with a vertical line written there. So that's the standard notation for denoting the set of all complex numbers. So in the course of your studies, you will see that C will be considered as the completion of R. Now, what is the completion of R? Now, go back to the question, why we need complex numbers. So basically, we started with the quadratic equation and we got stuck at some point, and we said that the roots of this quadratic equation are not in real numbers, they are somewhere else. So C is that somewhere else thing. In fact, C is that thing where all roots of any polynomial equation, that means any quadratic equation, biquadratic equation, 3-degree equation, all the roots of any such equation with real coefficient, that means the coefficients are real, such polynomial equations will have root within C. So R was not sufficient because the equations may not have roots within R, but C is something that's kind of a much bigger set, and it contains all such things. That means you can surely, you without any doubt, you can say that the roots must be in C within the set of all complex numbers. So it somehow it completes R in terms of solving polynomial equations. So that is why C is called completion of what? Completion is a technical term. You will learn more about it. Okay. So you know all these things. So let's come to the next thing, that geometrical representation of complex numbers. Well, so how a complex number looks like? It looks like a plus ib. So actually we can associate an ordered pair AB with every complex numbers. Complex numbers are A plus IB. So real part, imaginary part. So we associate a point, an ordered pair AB with A plus IB. So as we associate a point, so that point can be plotted in the two-dimensional plane. So we can associate a point in a two-dimensional plane with every complex numbers. All right. Now, if we plot and if you consider the points on a plane and vice versa, if you are given a point, you can think of a complex number corresponding to that point. Suppose this is the point AB, then you can think of a complex number of the form A plus IB. And reversely, if you are given a point complex number A plus IB, you can think of a point AB on the complex plane, on the plane. And if we are considering complex number and we are talking about a two-dimensional plane, then at that time this plane will be called a complex plane or an argand plane. So I haven't written that names anywhere, but it is now, it's called a complex plane. All right. So in particular, the point, that's the distinguished one, I, which is root over of -1, can be plotted at the point here at the on the y-axis and at the distance of 1 from the origin. And as x-axis was earlier considered as the real axis, now as I is plotted on the y-axis, so y-axis is now will be called the imaginary axis. So all multiples of I, that means 2i, 3i, there will be points on this y-axis. So y-axis is now called the imaginary axis, and x-axis, as earlier it is your real axis. That means all the real numbers are plotted here and all the multiples of i's are plotted here. And if you add them too, and you'll get a point here. So don't get confused and don't get overburdened. Just think of every complex number as a point on a plane. Now, if it is a point on a plane, that means it is at some distance from the origin. So suppose A is the point AB, which corresponds to the complex number A plus IB, and it is at the point, it's at the distance R from the origin O. Then clearly from your elementary coordinate geometry knowledge, you can say that this distance is A and this distance is B. So R is basically is this thing. It's a distance and it is given by root over a square plus b square. All right, it's a Pythagoras formula. All right, and this distance of the point from the origin, straight distance from the origin to the point, is called the modulus of the complex number a plus ib, of which the point is associated to. Okay, so if z is your a plus ib, then modulus of z will be this r, the distance from origin to the point. So it is root over a square plus b square. You must be knowing all these things. These are pretty elementary stuff. The next thing, have I skipped anything? No, I haven't. Well, the real numbers, so far you knew about the addition of real numbers, multiplication of real numbers, and other such operations of real numbers. You are familiar with that. Now, complex numbers are some other numbers. They are not real numbers. So they must have some algebraic properties like addition, multiplication, subtraction, and so on. So what are these properties of complex numbers? So addition is defined among the complex numbers like this. If you add a plus ib with c plus id, then the real parts are added together and I into the imaginary parts are added together. It's pretty simple. And So for the multiplication is concerned, it's like multiplying these two. If you multiply a plus ib with c plus id, then ac minus bd, that means b into d into I square is minus 1, so ac minus bd plus I into ad plus bc. All right, so this is the addition and multiplication thing. And if you multiply a purely real number to a complex number, say alpha is a pure real number, and if you're multiplying it to a complex number, then it simply alpha a plus I into alpha b. It's a very elementary derivation from this point to this point. Alpha can be thought of as alpha plus 0 into I. So it elementary follows from this formula to this. Now, suppose Z1, Z2, Z3 are complex numbers. Then if you multiply Z1 to Z2, the same thing we will get with if you multiply Z2 to Z1. This is a very distinguished property, which is still looks very obvious for you because so far you have worked with the real numbers, and this property is called commutativity, and it also holds in the case of complex numbers. So if you flip them, the value of the multiplication doesn't change. And if you multiply Z1 to the Z2 plus Z3, then this Z1 actually distributes over the addition, and it gives a result like this: Z1 into Z2 plus Z1 into Z3. So as if the multiplication is getting distributed over addition, and that's how the name came. And it says the property is called the distributive property. All right. So these are the algebraic operations on complex numbers. Fairly simple. And in the complex number case, you have another thing which was not there in the case of real numbers. That is called the conjugate of a complex number. So if you have a complex number z, say a plus ib it is, and then you can associate another unique complex number. Now, unique complex number means if it is for a plus ib, then you will get only one number. So you cannot get two numbers corresponding to a plus ib. So you will get only one complex number, namely a minus ib. That is called the conjugate of z, and it is usually denoted by z bar. Bar means a line on the top. So this is called the conjugate of z. Now how it looks like in the case of if you consider a plus ib as a point. If you consider a plus ib, this complex number, as a point ab on the complex plane, then the conjugate is merely the mirror image of the point ab, where the mirror with respect to the x-axis. That means if you set up a mirror along the x-axis, and if you see the image of AB in that mirror, then the image will be at the same distance from the mirror. So this point will be the conjugate of the point, the complex number a plus ib. Well, fairly simple. Now there are certain properties that you can check yourself. These are easy to check in the case of conjugate, like the number one, modulus of z square is nothing but z into z bar. Now, well, z is, if you consider z to be a plus ib, then z is a plus ib into a minus ib, and if you multiply them together, you will surely get a square plus b square, and that is nothing but root over mod of that's a square of modulus. As you know, the modulus is root over a square plus b square, and mod of z is same as mod of z bar. They will have the same modulus. That means the modulus of a plus ib will be root over a square plus b square, and the modulus of a minus ib will be root over a square plus b square. So see this distance and this distance, they are the same. Okay, so these two are similar triangles, as this and this are the same, so this is a similar triangle. So these two distance, this is by the way, remember, you remember that this distance is called the modulus, the distance from origin to the point. All right, number 3, I have circled it in red. 1 by z, when z is not 0, can be written as z bar by mod z square. Well, this is fairly easy. You multiply z bar to the denominator and numerator, and you'll get something like this. Now, why I have circled it? Because this is a standard technique to deal with some complex number sitting at the denominator. To handle a complex number at the denominator, we have to pull that complex number from denominator to numerator, and we like to get a real number at the denominator. So this is how we get it. So see, now the complex number thing comes on the top as the numerator, z bar, that's a minus ib excuse me, and at the denominator you are getting merely a real number mod z square. Okay, this process is called rationalization, and this you will be using time and again, so you must keep an eye on this. Well, half of z plus z bar is the real part of z. Is fairly easy to check. A plus ib plus a minus ib will give 2a, and that's twice of the real part, and imaginary part of z is 1 by 2i of z minus z bar. Z plus z bar, if you add the two complex number and then take the conjugate, then you simply get this, that the value is simply, if you take the conjugate of individual number and then add them together. So first adding then conjugation is the same as first take conjugate of each individual complex numbers and then add. Z1 into Z2 bar is same as Z1 bar into Z2 bar. So multiply them, then conjugate is same as first take conjugate, then multiply. Okay, these are fairly easy things to check. So I'm not doing it. Let me see. Yes, I'm not doing it, and you can do it on your own. So I leave it as an exercise. Well, our aim is to go towards certain important inequalities, which are mainly deals with the modulus of complex number. To reach there, we need certain tools. So let us recall some more things regarding modulus. Well, if z is a complex number, then the modulus of z is definitely greater than 0. If z is 0, if z is not 0, and if modulus of z is 0, if and only if mod z is 0. Now first let me come here. Now when do we say a complex number as 0? It is 0 when both real part is 0 as well as imaginary part is 0. So basically a complex number 0 is a simple 0, but it is written as 0 plus I into 0, and that thing is called the 0 complex number. So if it is not 0, so at least one of the real part or imaginary part will be present there. Okay, and the root modulus, you know, the modulus is root over x square plus y square. If either x is present or y is present, even if it is negative or positive, irrespective of that, then the square of that will be here, and root over of that will give you something positive. So it will be definitely greater than 0 if it is not 0. And if x is 0, now let's come to this thing. Mod Z is 0 if and only if Z is 0. Now this if and only if, I have underlined this. This if and only if thing is a technical terminology in mathematical science. You will see it many times, many places, in many papers, many subjects, many topics. It actually means, let me write it down in this format. A if and only if B means A implies B. That means A will imply B as well as B will imply A. So that means in this case we have to show that mod Z0 implies Z is 0, and as well as Z is 0 implies mod Z is 0. Now if mod Z is 0 means this quantity is 0, root over of x square plus y square is 0. Now root over of x square plus y square is 0 means if you square them up, you will get x square plus y square is 0. Now x square and y square both are positive numbers. Sum of two positive number is 0. That means definitely each of the positive numbers are 0. That means x square is 0 and y square is 0. And then if x square is 0, then x is 0, y square is 0, will definitely be y is 0. So both real part x and imaginary part y are 0. So that implies z is 0. And if you do it in a reverse way, that's a very simple thing. If z is 0, then both x and y are 0. So root over x square plus y square is 0. So z is 0. So that is how if and only if thing works. Both way implication sort of thing. The next is modulus of z, z1, z2 is fairly mod of product of two moduluses. And in the case of if z2 is not 0, then the division z1 by z2 is division of the modulus. Now I have given you a hint, rather I have showed it whole thing, because you must know how to work with this. Suppose you start with this thing z1 z2, then modulus of square, we have already seen that modulus of square is the z into the is conjugate. So we have multiplied these and its conjugate. Now z1 into z2, z1 into z2 bar, whole bar is z1 bar, z2 bar. Now as the multiplication is commutative, that means if you flip z1 and this z2 here, if you flip them together, you flip them, then you can write, and the value will not change. That's the commutativity that we talked about. Then this is z1 into z1 bar, z2 into z2 bar, and z1 into z1 bar is z1 mod z1 square, z2 into z2 bar is your z2 square, hence the result. Now in this case, as I told you, that we have z2 at the denominator, when we don't like to have complex number at the denominator, so multiply z2 bar at the denominator as well as numerator. The numerator becomes z1 into z2 bar, and the denominator becomes z2 bar square, and hence we proceed. If you take modulus, then as this is a purely real number, so the real number can be written as a plus I into 0. So modulus of that is merely mod of a. So it turns out to be, and this is a positive thing, then mod of a, mod of this thing is the same as itself. So it turns out to be this, and then finally here at this point, mod of z2 bar is same as mod of z2, and now as z2 is not 0, z2 is not 0, so mod z2 is not 0, it is greater than 0, so we can cancel them and we get such a result. Okay, so these are fairly simple results regarding modulus. Now we are set to talk about the first inequality. Well, the statement is fairly simple. If you have two complex numbers z and w, then z plus w is modulus of that is smaller than the mod of individual thing. Well, how to start with this? Well, suppose z is a complex number, not this z, any complex number. Mod of z will be root over of real part square plus imaginary part square. So definitely that is real part is smaller than mod z. Okay, because mod z has something more than the real part. Okay, so it is less or equals to mod z. Similarly, imaginary part of z is something less or equals to mod z, because mod z is root over of real part square plus imaginary part square. So it is definitely less or equals to. Okay, well, if this is okay, then we can write real part of z omega bar. Now look at this complex number. Z and W are complex numbers. So we are now particularly looking at Z into W bar, this complex number. That will be, this real part of this complex number will be less than mod of this, and mod of this is mod of individual thing, mod of Z into mod of W bar, and mod of W bar is same as mod of W. So we are keeping it at our hand. Okay, this is an observation that we are keeping it at our hand and we are proceeding. Now z plus w mod of that whole square, and really this into this, and then distribute it over addition and then multiply them, and you will get something of this type. Z w bar and z bar w, and z bar w can be written as whole bar of z into w bar. Okay, now bar, conjugate of a conjugate is the complex number itself, you know that. So that gives you, if you add this and its conjugate, then you'll get twice of real part of this. Now you know that real part of this, you already know, is less than this quantity. So far we are getting equality. Now we are getting something bigger. We are replacing this part by a bigger thing. So it becoming an inequality, and this is nothing but this thing. So altogether we are getting this is small. This quantity is bigger than this thing, because at this point we are getting something, start getting something bigger. So this is less or equals to this. So we get the result. Now we can generalize this result for any finite number of complex numbers. So instead of two numbers, if you have n many numbers, so if you add them, z1 plus z2 plus zn like this, then the mod of that will be smaller than addition of individual moduluses. Okay, so this inequality has a general version, and this is useful, and we will be using them in future. So we are putting it in our recap section. Well, now again, certain geometric properties. Okay, well, we have noted how a complex number is plotted on a two-dimensional plane called the complex plane, and we also have learned there is something called addition of complex numbers, there is something called subtraction of complex numbers. Okay, now what is the significance of, if you add two complex numbers, then you are supposed to get a complex number. If you subtract one complex number from another complex number, you are supposed to get another complex number. Now, how these complex numbers are represented on a plane as a point. So as these two complex numbers are represented as a point, the starting complex numbers, then how the addition and subtraction complex numbers are represented with respect to these two numbers in a plane? That's the question. So that's a geometric interpretation of addition and subtraction of complex numbers. Well, it's a bit of a clumsy picture, but I request you to kindly enlarge it and see it, and it says a lot of things. This picture says a lot of things. Suppose we start with two complex numbers, z1 and z2. Okay, so let's plot them as points on the plane. So suppose this is a is your z1 and b is your z2 complex number plotted on the plane as points. Okay, now they can be anywhere, but I have plotted them here and here just to make the picture uh, clear so that you can visualize certain things. So that is why I did so. They can be anywhere, but the same picture can be drawn there. Could be a bit difficult, could be a bit complicated to draw, but it can be drawn. All I request you to learn the method. Okay, so suppose z1 and z2 are the two complex numbers given to you, and they are plotted at a and b point. All right, now you can think of, now z is a complex number, then how about minus z? Well, minus z means minus 1 into z. If z has, this is z's real part and this thing is z's, okay, sorry, this distance is z2's real part and this distance is z2's imaginary part. So minus z2 means negative of both things. So negative of this thing is here, comes here. So the real part negative comes here, and imaginary part distance, this is positive distance and it comes out to a negative distance. Here the real part is negative and it turns out to be a positive thing for minus z2. So if z2 is here, then minus z2 is here. These two distances are same. OB and OC are the same. Okay. So if z2 is here, minus z2 is here. Okay. You satisfy yourself. I mean that this is really minus z2. So now we have three things: z1, z2, and minus z2. Okay. Now join the origin to A, to B, and to C. Fine. Now we have two things, this and this. You complete the parallelogram whose adjacent sides are OB and OA, and you are getting a parallelogram like this. Okay, this is the parallelogram. Note that, and then you draw this diagonal. Then this vertex of the parallelogram represents the complex number z1 plus z2. Okay, this complex number, this point represents the complex number z1 plus z2, and modulus of that merely is this distance, the length of this diagonal of this vertex. Okay, and also note certain things, as this is a parallelogram, so this distance and this length are the same. So if this is your mod z2, so this will be your mod z2. Okay, just keep it noted because we will be needing it soon. And now here we have another two sides, OA and OC, and I would like to complete the parallelogram here also. Okay. Now, as this is a long line, so the two parallelograms merely adjacent to its adjacent, and they are connected by this line OA. So here we have a parallelogram, and now we draw this diagonal. This diagonal, the end point of this diagonal, that means this vertex of the parallelogram represents this point F, represents z1 minus z2. So if we start with two complex numbers Z1 and Z2, then now we have found 2 points E and F on the plane, which represents Z1 plus Z2 and Z1 minus Z2. That's the geometric significance of addition and subtraction. Okay. Now come here in this parallelogram again. I join this diagonal with the dotted line. I have joined this the dotted line with the pencil line, so slightly faint. And note that, and think of these parallelogram BAFO. This is also a parallelogram. Okay, BAFO. This is also a parallelogram. Now BA is merely the distance between the two given complex numbers. Why I am considering it? Because one of the side BA or AB, whatever you say, it's merely the distance between two given complex numbers Z1 and Z2. That's a difference between two complex numbers on the plane. And as this is a parallelogram, so that must be same as OF. So the distance of Z2 and Z1 is nothing but this distance, which is merely the modulus of Z1 minus Z2. So Z1 minus Z2, the distance between the two given complex numbers Z1 and Z2 is merely given by mod of Z1 minus Z2. Okay, so that is why this picture is so important. We will come back to it again. All right, so please remember this picture. I would request you to remember this, because the next inequality actually, this picture actually proves this next inequality. Well, the next inequality says, for each pair of complex numbers Z1 and Z2, we have mod of mod Z1 minus mod Z2 is less or equals to mod of Z1 plus Z2. I would like to request you to kindly write down this statement at your notebook, because anyway, I have to go back to the picture once more. All right. Anyway, you have this note. I have circulated this lecture note also, so there you can manage to see the picture as well as the write-up. So I should have drawn the picture on this page, but somehow due to space problem I couldn't. Anyway, let's come back to the picture again. Okay, before that, now mod Z1 is a real number, mod Z2 is a real number. So subtraction of two real number gives a real number. So this part is not a complex number. This is not a complex number. This part is merely fully a real number. So modulus of that, modulus of a real number. Now, modulus of a real number. You must be knowing mod of a real number x is x if x is greater than or equal to 0, and it is minus x if x is less than 0. Okay, you must be remembering that. So with that thing, we can write this modulus is merely the same as itself. It's mod Z1 minus mod Z2 if Z1 is greater than or equal to Z2. That means this is positive, and this is reversed minus of that when Z2 minus Z1 if Z2 is greater than Z1. Okay, so that's the usual real number modulus formula. Okay, so now we have two cases, this case and that case. Okay, now we will prove this inequality for both cases. So if for this case, that means Z1 is mod Z1 is greater than Z2, we have to show this is less than this thing. That means we have to show mod z1 is less than this plus mod z2. Just put it here. Okay, switch the side, and in this case it turns out to be mod z2 is less than this plus z1. Okay, now please remember them, and I'm going back to the picture once more. So the what the quantities we are having, we are dealing with mod z1, mod z2, and mod of z1 plus z2. These are the three quantities we are dealing with. Fine. All right. Now let's come to this picture. Here, look at this triangle OAE. Here we have already noted that OE is modulus of z1 plus z2. Surely it is, because E is the point z1 plus z2. So OE is the modulus of z1 plus z2. OA is mod of z1, clearly, because that's the definition of modulus. And AE is mod z2 because it's the two parallel sides of a parallelogram. So OB is z mod z2, so it must be of the same length. So AE is mod z2. So now we know all the lengths of the triangle OAE. And you must be remembering the famous result that sum of two sides of a triangle must be greater than the third side, greater than or equal to the third side. So if you add this side and this side, it must be greater than this side. That is your this thing. And if you add this side and this side, that must be greater than this side, and that is your the first one. So the both cases are true by the triangle inequality. So in both situations, this result is true. So hence the inequality follows. So that's a pictorial kind of a pictorial proof of a result. Okay, that's another way of you must note this thing, because that's a geometric proof of a complex thing. Okay, so sometimes geometry comes to help you to prove certain things which are not geometrical. This inequality is not a geometrical thing. You don't see any geometry written over here, but you can surely bring geometry to solve your problem of complex numbers. Okay, that's the beauty of the subject, that there are certain weapons and you can bring whatever weapon you like to solve another thing. Okay, so you have, these are the weapons you are using: the geometry, the complex numbers, the real numbers. So in this case you are using the geometry weapon to solve this problem. Okay, so everything is fused together. Well, we will end the class with certain important equalities. Now no more inequalities, the two inequalities are gone. Now we end this class with two important equalities, because they are important from the point of view of the examinations. These are the common things. So that's the first one. For any two complex numbers, this guy is nothing but this guy. Okay, so it's more like a plus b whole square plus a minus b whole square is twice of a square plus b square. You know, that's a complex version of that result. But how to show that, because that's a real number and this is a complex number. So let's start with this thing. It is nothing but z this into its conjugate and multiply them together, and you will get a result like this. So pardon me for making a mess here. So it's nothing but mod z1 square plus z1 z2 bar plus z2 into z1 bar plus z2 square, mod z2 square. And similarly this guy can be written in this format. Now simply add them together, then you will get the equality. It's fairly easy one. Well, the next one looks a bit complicated, but it's very basically simple. See, if A, B are complex numbers, okay, very unusual to write a complex number like A, B. Usually we write real numbers as A, B. So if they are notation, so if A and B are complex numbers, then show that this thing happens. This equal to this. This is a much longer expression, but it turns out to be this is simple this thing. Well, for simplicity, let's denote this and this, and now start with this thing. This is nothing but square of this object, square of the left hand side of this inequality. If you do it, you will get square of z, square of this, and multiplication of this. Now, product of two mod is same as mod of the product. So you do the product thing, and if you do the product thing, you will see this is a plus root over this thing into a minus root over this thing, and this is a plus something, a plus b into a minus b is root over a square plus b square, so that merely gives you b square, and you are left with this, and you write down these things. Now, what is this proof is easy, but what I am emphasizing on is there are certain steps you are using, and at each step you must write an explanation for that. Here, why are you performing this? Because you are applying this result. This is a result for complex numbers, and at this level you are basically applying this result, the result that you have proven here. So you have to write them as a side note while at the examination hall, because the examiner will definitely look for them. What are you doing and why are you doing? So that is why I have emphasizing on this thing. Otherwise the proof is easy. So I request you to go through these proofs and try it with your own hand, and that's all for the recap thing. So in the next class we will start with the polar representation of complex numbers, and if we need anything more to recap at that time, as when needed, we will recall them. Okay, that's all for today. Thank you very much, and I will be uploading the lecture note as well as the lecture. Okay, thank you very much.